Hey there peeps, let's take a look at a case where we have an elastic collision in one dimension and both the objects have velocity headed towards each other. It's a head-on collision. How do we handle it? Okay, let's take a look at the situation. Here's our coordinate system. The right is positive x, okay? So m1 has a mass of 5 kilograms. v1 naught is 10 meters per second, positive, heading towards the right. We have, on the other side, m2 is 2 kilograms, v2 naught is negative 3 meters per second. It is heading to the left, and they are going to smash into each other in a fully elastic collision. What's going to happen? What are v1 final and v2 final going to be? Let's recall that our derived equations, they work for the cases where the object is stationary. So what can we do? Okay, so we could either rederive those equations for the more complex case and do even crazier algebra than is on the notice bien in your notice folder, and come up with some kind of a grander version that handles the case where we have both the objects in motion. That's really difficult. I don't suggest doing that right now. We could instead utilize stuff we already know. We can go to this, changing our frame of reference. We will use relative velocity. So here's the strategy that's very clever. We will transform this problem by setting one of them as the stationary frame of reference, the fixed frame of reference. Let's do v2 naught, this one over here. Let's consider that because the derivation says v2. Let's call that v2 naught as the stationary object. All right. So here's what happens. In order to get this to be 0, we need to add 3 meters per second here. If we do it here, we also do it here for v1 naught. And so that means v1 naught prime becomes 13 meters per second. Notice that I put these little marks there. They look like apostrophes. It's called a prime mark. It's to distinguish the fact that we've shifted our frame of reference to something new so that we can realize when we look at it, that's not the Earth's frame of reference. That's the frame of reference now taken from being inside m2 as the stationary object. So let's see what happens when we crank this out in the next pane. All right, in this learning pane, that's P-A-N-E, not P-A-I-N, if that's what you were thinking. Although this is kind of a pain, but we'll make it as easy as possible on us. Okay, here we go. What we have is v2 naught as 0 meters per second, as established before. We have v1 naught as 13 meters per second. And we're going to run through and perform the calculations based on the derivation that we can use where one of them is stationary, right? This is stationary from this frame of reference. So v1 final prime equals v1 naught prime, and m1 minus m2, m1 plus m2, that stays the same as before, okay? So when I crank that out, that becomes 5.5 meters per second in this prime frame of reference. We go to v2 final prime equals v1 naught prime, 2m1 over the sum of the masses m1, m2, and what we get is 18.57 meters per second. Very, very important is that we have to change back to Earth's frame of reference. We can't keep it as 5.57 or 18.57 because then the principles of conservation of momentum and conservation of kinetic energy will not be upheld. We're going to check that later to see if it actually does when we change back our frame of reference. Let's do that. So we added 3 meters per second to each, so then we will subtract them here. Negative 3. So v1 final is actually, according to the Earth's frame of reference, 2.57 meters per second. According to the Earth's frame of reference, v2 final is 15.57 meters per second. Okay. Conservation of linear momentum, conservation of kinetic energy. These are just going to be little checks to make sure that everything's cool. What that means is that the first side of the equation is going to be equal to the other side. So original equals final. Here's the original side. m1 v1 naught plus m2 v2 naught. Here are the numbers. m1 v1 final, m2 v2 final. Here are the numbers. Both come out to 44 kilogram meters per second, momentum is conserved. In the case of kinetic energy, it's 1/2 mv squared. So we have m1 v1 naught, m2 v2 naught, m1 v1 final, m2 v2 final. What we do is we add the kinetic energies up, and we get 259 joules. Note that here, because of the negative, and that fact that momentum is a vector, what happens in that case is that this actually subtracts, right? But here, because it's a -3 squared, that becomes positive. So energies just add together. That is section, I believe, 7.6 in your book. Covers the fact that one is a scalar and one is a vector. Vector being momentum, scalar being this puppy right here. Energy. All right. Whew. Some chaos going on down there. But we got it. Morad.